Bueno, buenas tardes. Gracias por la presentación, lo cual me evita el presentarme a mí, que no me gusta nada.
Thank you very much for introducing me. Just like to say that I lead the Cybersecurity Laboratory that belongs to the BBVA group, where we do many things that are lots of fun. So what are we going to speak of? The title, the heading is quite ambitious because it's called Advancements in Machine Learning Applied to Cybersecurity. I have an hour, so what I'm going to do is to try and do away with the myth of what AI is not good for, and I'd like to tell you what it is good for. So I'm going to summarize how to attack machine learning algorithms. So we're going to make a trip around these things. So what are we going to do? This is a very quick introduction to AI, even though it's true that I speak a lot about AI, but in any case I've had to learn some things on cybersecurity, and I'm going to give you a very short introduction regarding the context of artificial intelligence, and then I'm going to tell you about things you cannot use it for. That is limitations, many of which lie on defensive security. And then I'm going to speak about offensive security, which is where we see there are more advancements now, formalizing of artificial intelligence from the point of view of security, and then conclusions. So what are we going to do in the next 58 minutes? We're going to try and do away with myths regarding artificial intelligence and applied to cybersecurity. Is AI of any use? Well, it is, or else we wouldn't be speaking about it. On this slide, we can see the different techniques that are learned, like supervised learning, non-supervised, and reinforcement, and the traditional things like image classification, recommendation systems, etc., etc. So here we have a large part of domains where it would be interesting to use artificial intelligence. And in fact, it's very interesting, and this chart is very well known. And by the way, there's a multitude of companies that are trying to apply AI to their own domains, because thus they can achieve an advantage, competitive edge. If you look at this chart, the part on security is very small. There are many scenarios where AI is very useful indeed, but in security there are very few companies specializing in security. Some companies are trying to apply it, but there are not many companies that specialize in drawing the potential of these algorithms applied to security. And now let me move. Well, there are some areas that are of great concern regarding AI, and I've related to this as to whether this software can be controlled by humans, if they could reach a stage where they would be harmful for humans. Right now, a few pictures of scientists who are working with artificial intelligence. Well, some of them are well known. They teach in Stanford, etc. Well, at least some of them. And one of the main problems is that right now we have to regulate the way in which these algorithms are used to see if we can cope or manage the moral component in order to see whether these algorithms are going to be good or not. There are many cases how AI imitates or replicates the negative attitudes of humans, like racism, etc. And this not only affects the net safety, but this is also related to society and the economics. And there are many people that are proposing a universal sort of income, so that by the time that the AI is more developed, those people who won't be able to find a job will be able to get an income via taxes paid by artificial intelligence. This sounds like something out of a movie, but nowadays we have many other problems. Perhaps tomorrow we won't be murdered by a robot, but there may be other problems such as wars between different cultures, and the problem is that we need artificial intelligence in order to solve more real problems that will affect us as a species. So obviously, we cannot do without AI. We need to develop it more and more, even though we run the risk of reaching a point where we won't be able to control it. And in fact, when we speak about the rapid pace of evolution of AI, we tend to show pictures like this of algorithms. Here we have several examples. Here we have a game at the top, and we can come up with specific algorithms that in specific tasks will achieve better outcomes or results than humans would reach when solving specific problems. This is the AlphaGo Zero. So AI will be substituting humans in some areas, but the true thing is that this is not all the way true. And we speak about singularity, this precise moment where an artificial intelligence will be able to perform better than humans at a specific task. The problem is that there's a lot of uncertainty. Nobody knows when this is going to happen. It is bound to happen, but we don't know when. The most rigorous study that we've found that tries to establish some possible scenarios when this will happen and things that will impact us as a society. So what this study says is that from now till 40 years ahead of us, many things will be substituted by AI. Here, for instance, the ability to write a book as a human would do it by the year 2049, writing a book by 2050. Well, different scenarios, for instance, replicating the performance of a physician and other tasks. So in 45 years, AI supposedly will be able to solve some problems that only a human being can solve. Now, this is an opportunity, but also a risk if we don't handle this adequately. So these are things that people, technicians and specialists in technologies are dealing with right now. We don't know how much money major companies are spending in developing this technology. AI has evolved a lot in the last decade because there are many companies investing huge amounts of money in this area. And in fact, there's something that I'd like highlighting. Everything related to AI is considered like the atom bomb. And there's parallelism with the Manhattan Project, when experiments were done at the beginning with this energy that they were afraid that they would burn the atmosphere. And the same is happening with AI. We've detected technology with a huge potential, but we still don't know whether we'll be able to handle it. So major powers are investing in these technologies, because supposedly in the next few years the economic, social, and military impact is going to be huge. And this is related to the introduction of machine learning. Many people speak about machine learning. There are some very good courses. Last year in CyberCamp there was a very interesting talk on this issue, and I have about 50 minutes ahead, and I'd like to touch upon some issues related to AI plus machine learning and applied to the world of cybersecurity. The first slide has to do with working without complex. Many people here, I'm sure, have no idea how to apply machine learning to cybersecurity, and possibly nobody knows how to. And there's a sentence I really like, and that is part of all this marketing strategy around these technologies applied to the field of security. It says everyone talks about it, but nobody really knows how to do it. Everyone thinks everyone else is doing it, so everyone claims they are doing it. And so there's a whole scenario of uncertainty where we don't know whether this technology is contributing with some differential sort of value. So in the next few minutes I'm going to try and give a few brushstrokes this issue, about this subject, in order to see whether we can solve this problem. In fact, there is something we should reflect upon, and that is whether AI may solve actual cybersecurity problems. Let me read to you a paragraph of the publisher of this journal that says, "This is a world where mass amounts of data are replacing any other tool that could be applied. Let's forget about the human behavioral theories and linguistics or sociology. Let's forget about taxonomy or psychology. Who knows why people do what they do? The important thing is that they do what they do, and we can do a follow-up and measure it. With enough data, figures speak for themselves." And this is an opinion by the publisher of this journal, and I'm against this. I oppose this opinion. I believe that there's a human thing to this that contributes with differential or added value that AI won't be able to provide, or at least not in the next few decades. And there are many stories, many articles and papers that speak and justify the existence of many scenarios where a human component provides or contributes with an added component where these AI systems fail. There are other scenarios, though, where AI can simply not be applied. Imagine that in cybersecurity we have the best possible algorithm in order to identify a user or an attacker, but then there's a law, there's a rule that prevents us from applying that procedure, and it doesn't matter whether it's good or bad, we simply cannot apply it. And in this slide I'm giving you an example in the case of giving a loan, a bank giving a loan, and here we cannot use a machine learning algorithm. Well, why? Well, because due to the data protection law says that those decisions that may have an effect on the life of citizens must be reasoned and consented and revised. This means that if you know anything about AI, we have some environments where we where we are trained. There are some entries, some outputs, and we don't know how this output has taken place. We don't know why. So there are scenarios where this is simply not possible. That is, we need to be able to negotiate. There needs to be a negotiation between an entry and an exit. In terms of security, privacy, identification, we need to bear in mind all of these things, because even though algorithms work, we wouldn't be able to do anything about this. And this is the example that I wanted to tell you about. This is a research we did, I don't know, 3 years ago. And this is a very specific example. This was malware detection issues in Android with AI in this case, so we started using AI in order to detect everything, in order to detect malware and many other things. And it was going well, well characterized. That worked halfway well, but we needed more accuracy in order to work like a human analyst would. So in the case of Android applications, we saw that there were certain elements that were a differential advantage and made this model work better. There's this example on the left. And we realized that by using natural language processing techniques, we realized that an attacker, when publishing malware in the Android market, his or her description had a very poor linguistic quality, using very few words, not many adjectives, verbs, but a company who did legitimate applications did better descriptions, that is, longer descriptions and much better written, much richer language. So this proves that the human component is still makes a difference compared with AI, which could be an addition, a complement, but by no means is it a solution. So what is actually being done in machine learning applied to cybersecurity? Well, I think machine intelligence is useful for defense, not offense, says Shamir. And so what I'm going to show you right now has to do with public information that's known from companies and academic studies. And part of this talk is justified by this person. Do you guys know who this is? Please raise your hands if that is the case. This is Shamir. And in one of his last presentations or conferences, he said, I think machine intelligence is useful for defense, not offense. And this is a sentence that was very important for me, because Shamir is possibly one of the most brilliant people on earth, and I was surprised by this, because in the presentation we're going to see that offensive security is what has evolved the most, unlike a defensive security. So what is AI used for right now when speaking about security or defense security or defense? Traditionally speaking, normally it is used for detecting fraud, malware, everything related to analysis and monitoring and variant, and more in everything related to authentication.
Control de acceso, pero bueno, hay muchos otros.
There are other scenarios where it would be very interesting to use this, like in the development of software, and this is the normal scenario where all the major companies want to contribute with their own thing using AI. This is the normal cycle that is always presented, algorithms, a training process, identification, etc. So what public information exists in this field? We go to companies, and more we start seeing projects that are starting to distribute tutorials and information focused on defense security. We have MLSEC, for instance, where we see the work by many researchers. And Most of these proposals focus on two things, basically. On the one hand, traffic analysis and network monitoring and everything that has to do with malware detection or preventing malware from exploiting certain characteristics. As you possibly know, these proposals, major suppliers, major technological companies or security companies are trying to use these algorithms with their products. But in many of these cases, as we shall see later, technology is not that disruptive. That is, these 20-year-old proposals with 20-year-old algorithms, which perhaps do make a difference somewhat, but they're not associated to the sort of marketing related to these proposals. This is an example of companies that have greater potential from the point of view of AI. Here you can see a small square in red where we can see some of them focused on cybersecurity and AI. Here, something silence. We see the names of the companies plus a couple more. I don't know if you can see them. And basically, countries that work in this area is the US, UK, and Israel. These are the three most important countries that work in this section, in this area. And they basically work on network monitoring and everything related to preventing software from exploiting certain behaviors. So what prevents us from applying real AI? Well, I'm going to summarize these things. On the one hand, we see the amount and the quantity and quality of data. If any of you uses AI, probably I could ask you a question: how many data do we need in order to train a system? Answering this question is difficult because the answer normally is the more the data, the better, but that's no scientific answer. What do you mean by the more data, the better? So I guess it depends. It depends on the quality of the data. What does this mean? How do you measure the quality of the data? These are abstract things. And if we apply this to cybersecurity, this makes things much more difficult, and it prevents us from detecting certain attack vectors. For instance, a threat we've never seen. What do? We normally do a profile of the normal behavior. And if it deviates from this, it means that this behavior is related to a human. So from that point of view, and conceptually speaking, we are still working like we used to 20, 30 years ago, so we haven't evolved beyond white or black lists. And there's another thing that's very important, and that's related to static training. Normally in artificial AI, people train systems and they apply them. But if we go underneath and if we go deeper into this actual training or real training, is not an ongoing training. And by this, I mean that these algorithms would learn as they go, but with an important nuance. And that is that this training has to bear in mind the presence of an active attacker. That is, the actual proposals that are being worked on is having an intelligence that works, but with the presence of an attacker that will make your model succeed or fail. And there's a couple of more points that we'll be developing more in depth and that are really important. On the one hand, everything that's related to the privacy of algorithms and models. When we use AI, we develop a series of models, and these models, where do we publish these models? Can somebody steal them? Can somebody manipulate them, which would affect the security of our systems? The answer is yes. And this is something we'll see very quickly. And a couple of issues in the end. And that is that offense security exists in AI. That is, today it is possible to manipulate AI algorithms that are used in defense in order to provoke different scenarios, like I will show you. But normally these are targeted attacks or mass attacks. There are major institutions like DARPA that are willing to give lots of money to those who can define AI systems that will be able to learn in an ongoing way, but in the presence of an attacker. And the role of the attacker is to make this system fail or not work. And if somebody has the solution to this company will be delighted to give them lots of money in order to work on this. So when we speak about the real defense and offense security, we need to understand what's a generative adversarial network. Basically, we have a discriminator that acts like what's in charge of defense that makes a decision. And on the other hand, we have a generator that will trick or fool the system. So what the generator does is to enter information to the discriminator, and so the generator is going to be learning as it goes. And on the other hand, the discriminator, based on the samples it receives, it learns, so it will learn more from the attacker. And this is the actual scenario that's worked on with in AI, where an attacker can attack a system trying to beat it. And in defense security, well, this is a very complex scenario for which there's no ideal solution, and many of the existing ones are still being studied on a theoretical level. We don't have a lot of time, but I'm just going to show you a couple of examples in the area of defense security, but which I believe are interesting, apart from the network monitoring ones or malware detection. And this is related to data protection. And I'm going to speak a little bit about cryptograms. I'm going to show you a research done by Google a few years ago. And the headline said that they were able to use single-use algorithms, cryptographic single-use algorithms. We have this system like the one I showed you earlier, whereby Alice and Bob want to encrypt an information. In this communication, we have the presence of an attacker, which is a neural network. So Alice and Bob, without saying anything, or because of the way that the network is working, they detect the presence of an algorithm, and the algorithm is such that the attacker cannot decipher it, and a human being wouldn't do absolutely anything.
What is the problem about this? Well, if a human being sees this is basically an XOR. That is what is being calculated. It is a very interesting proposal, and it may entail a significant change in cryptography. Here is another example, a quick simulation we've made of this attack. Basically, we have a GAN scenario where one of the neural networks is able to create digital pictures that look very much like pictures of celebrities, for example, and in that process of deceiving the detector, it is hiding information behind the pictures. It also includes an additional component that tries to detect whether the information that's been hidden is well hidden or not. The deduction of this study, which is more interesting than the one we showed before, is that with this GAN system with neural networks, we can create new algorithms which are more robust than the ones that we have now. If you have the chance of taking a look at this research and you know a little bit about steganography, you will be able to value the importance of this study. This is what we've seen about defensive security. Now, regarding particular problems, an issue here is the privacy of models. Where do I publish models, and can attackers attack me? This is something we will understand in a few minutes. What are we trying to do in order to protect that scenario? Well, cryptonets are being researched, which is the fact of creating ciphered AI, creating cryptography and apply it to neural networks. So, if we are creating a training model with Amazon and someone is able to steal our model, that model would be coded. That's how the attacker wouldn't be able to draw our knowledge from there. Only users with a cryptographic key would be able to use it. If this ends up working in a more professional way in the future, stealing training models will be an issue that may be solved in the future. And what we said in the beginning, one of the main problems in cybersecurity is that sometimes we try to detect some things where we have very small samples of information from. That is, the samples we have are scarce and they aren't enough in order to make an identification. Will we be able to solve that problem? We don't know. There are other domains of application where a solution has been found. For example, in robotics, there is one-shot learning, which is applying models with just one sample. This is what can be done in certain scenarios. In robotics, a robot sees just one single example and can replicate that behavior. Then, for example, in terms of languages, there is the self-learning. For example, this is what Google does when it comes to a new language. The system is able to understand a new language without any training, without any samples, learn and replicate that language. Are we able to do that in cybersecurity? Not yet. Will we be able to do it? Well, we don't know yet. These are challenges we're currently working on. When we focus more on offensive security, we will talk more closely about machine learning and how software and hardware need to be understood as one more element in our industry and included in pen testing, software development, etc. In other words, AI is one more element that needs to be included in our industry. Well, this was a brief introduction. Now we're going to focus on the advances in terms of offensive cybersecurity. Here's where the greatest progress has been made. I'm going to tell you about 4 different types of attacks we know of. The classic attacks, which is using AI in order to do what we usually do with other tools or pen testing or hacking techniques, but in an improved way. Then synthetic systems that attack machine learning proposals. Another type of interesting proposals which have to do with applying machine learning to defensive security based on machine learning. And then a 4th category where everything goes into. We will see how we can steal AI models and how to introduce backdoors. It's important to focus on the picture we have on the top right corner here. If you are into pen testing and Blackbox pen testing, for example, this is very similar. Think about that scheme and think what an attacker would be able to do. If an attacker can access only the inputs, the entrances, what can they do? And if they can only access the outputs, what can they do? Using that logic, we can create attacker models and build better systems in order to avoid attacks. We will now see some examples of each. When it comes to classic attacks, here you have a couple of examples. The first one is PassGAN. It's a tool that's ready for use. Imagine someone steals a password dictionary from LinkedIn or a different network. Then, using neural networks, you send over that list of keys, and this proposal is able to create a cracking rule, a rule that will not only match with the keys it's seeing, but with other similar keys as well. So what is this for? This proves that with this technique, we can hack passwords more efficiently and quicker also. And this is the proof of that, because you can generalize the rules and then apply them in future incidences. This is an example of the last DEF, where neural networks were used in order to create SQL injection attacks. When you have the rule already, instead of following your own criterion or using the brute force, you can reduce the number of requests to the server in order to crack that database. So this is the way of improving traditional hacking tools with neural networks. Second type of attacks, synthetic attacks. This is very well known. It's been on the press many times, but we have to underline that it is more and more complicated to tell real information from unreal information, particularly in audio and video, because systems are getting more complicated and they are able to falsify, to forge systems. Here, somebody with a pair of modified glasses can trick the system so that it can mislead faces. Here's another example of how to manipulate a video in real time. Here you can see how the gestures of the actor on the screen can be changed by using this program. They've used this with many celebrities, including Schwarzenegger, so I encourage you to take a look at it. Then there are other programs to replicate voices with just a sample of 30 seconds of somebody's voice. It is difficult to tell from the human ear what the real speech is and what the unreal or fake one is. And this is the kind of attacks that are becoming more and more popular. Now, the third type are the offensive attacks that I think are more interesting. There are three types of attacks: evasion attacks and poisoning attacks. The first one has to do with how to evade a classification mechanism that's already established. For example, if our antivirus classifies between malware and goodware, we can make the antivirus classify malware as goodware and the other way around. When it comes to poisoning, it is about introducing poison into the systems so that they can perform particular actions. Now, talking about offensive attacks, here we have another example of a defender and an attacker competing at the same time. There is a lot of literature around this, many from the academia, having to do with mathematical formulae. Well, if you're interested, we can delve into that, but we won't do it today. But the goal, my point is that there are libraries that people can download attacking models in an actual way without reading a lot of manuals and without being John Nash. So clever hands in deep pawning are the most developed ones, particularly clever hands, of which I will show you some demos now. And then we also have deep pawning, which was presented as the Metasploit for machine learning. It was a very promising tool for attacks, but it's true that they haven't updated their GitHub for a few months. So if the project isn't dead, it is close to death anyway. Now I will show you some example of some significant attacks, the most representative ones from clever hands, and then you will see some videos showcasing a little bit the type 2 attacks. I will try to simplify it with human words as much as I can. So these attacks provide two scenarios, Whitebox and Blackbox. In Whitebox attacks, what the attacker needs is to know the entire training model and all the configuration parameters. This may not be very realistic, but you need to have all that information. Once you have it, you need to introduce inputs into the model and get its outputs. So you know the configuration, you add inputs and obtain outputs, and with that information you're able to generate adversarial examples that may lead the system to misclassify. This means two things. First, the ability of performing massive attacks. Imagine that a classification system can detect numbers from 0 to 9. I input 9 or 10, and I want the system to classify it as something different than a 0. It doesn't matter where. For example, in malware, I don't want it to classify it as family, but as a different thing. This is what we call a massive attack. On the other hand, targeted attacks are different. I introduce a 0, and I always want it to classify it always as a 2 or always as a 9. So depending on the system, we will be more interested in a massive or in a targeted attack. Now, the interesting thing here are black box attacks. They've been widely developed in 2017. What do they enable? They have quite an important potential because we don't need to know anything about the artificial intelligence system. There is a system in Google enabling AI, and I don't need to know it. I don't need to know its configuration. All I need is to make some requests. That is, put in some inputs and obtain some outputs. That's perfectly feasible. And these attacks are usually against Google, for example. So what we create is a replacement model. It's as if I could create a model at home without knowing anything about the system I want to attack. Once I have my model, I can do the tests in order to know what inputs I need to put into the real system in order to generate targeted or massive attacks. That's why black box attacks are very useful and in practical terms can be applied to any AI system. We don't have a lot of time left, so I will be pretty brief here. This is an attack from clever hands. This would be a white box attack. This is the simulation. I would like to deal with it in more depth, but we don't have time. Here you have a few pictures. And you can see a lot of numbers running through. On the left you have some noise, and on the right you have what the classification system would see. Here are several examples, and the final table, that's a summary of it all, and that's the interesting part. So what does this mean? What is this table about? We have a scenario where the attacker knows the model and the configuration parameters. We have inputs and outputs, and our goal is knowing what we have to do at the input in order to make the system react the way we want. This is what a targeted attack would be like. For example, on top we have 10 columns from 0 to 9. So this silly example classifies 10 numbers. Imagine we input 0 and we want the system to identify 0. So we introduce our input and leave it as it is. Now imagine we input a 0, but we want the system to classify it as a number 1. So if you look to your right, you will see that that 0 that we introduce will incorporate several alterations in order to classify, to make it be classified as 1 or as 2 or 3. That is, we can create this table to know which input and which perturbation is input in order to have a particular output. What does this mean? In many cybersecurity environments, Whitebox attacks and Blackbox attacks allow you to do this and make the classification system fail. So this is a current challenge now in offensive security. The number of requests that you have to do to real system needs to be as reduced as possible. For example, many techniques are able to trick Google or Amazon's classification systems with only 800 requests. With that, you can create your own model, train it, and if you want to perform a targeted attack, you know the table you need to use in order to yield a particular result. Here are some other examples with the other tool I was telling you about that hasn't evolved much, but the basic idea is the same both for Blackbox and Whitebox attacks. And if you have time, I would recommend you to read this paper on how to perform Blackbox attacks on artificial intelligence systems. It has a great potential because you can generalize this to any algorithm of AI. Type number 4, this is a little bit of everything, and I'm going to underline just two. One that has to do with model stealing, and another one has to do with backdoors. What's been proved is that in many cases, we either know everything or try to approach it to inputs and outputs, creating our own model. In these attacks, we just try to steal the original model that Google or Amazon is using. How can we do this? Well, there are many ways. I'm going to give you an example. Please don't be scared. This is a very basic formula, which is the logistic regression formula, one of the multiple algorithms we have in order to create artificial intelligence. How can we attack the system and steal the model? For example, the model that Amazon is using. Well, in this case, we need to introduce queries and obtain the responses X and Y. If we have this, we just have to replace in the equation X and X plus B, and with this we will obtain enough number of equations. For example, we create 100 queries for 100 equations for 100 queries. These are normal equations we all learn in high school. So once you solve the equation, you would have all the configuration parameters of this area. So with input petitions, input requests, and with the outputs, that would be enough to copy, replicate, or steal those models. As I said, from Amazon or from Google. Here is more information if you are interested in knowing more. And the last attack I wanted to talk to you about was the introduction of backdoors in AI algorithms. This starts from the idea that people tend to share their AI algorithms more and more in order that other people can use it. Now, technically, we can use backdoors in different ways. What do we understand by backdoor in this scenario? For example, if we work with neural networks, it is about introducing more neural networks so that the system continues working normally, but it now has an additional channel that makes the system work otherwise. This is, for example, useful for the systems that classify traffic signs. If this mechanism that controls traffic signs had a backdoor, we could use a small sticker or a mark so that the car would stop instead of accelerating. This is really serious, as you cannot control it. There is an additional problem here, which is called transfer learning. I will give you an example. Imagine a university or research center develops an algorithm that is able to identify objects in general. They publish it on the internet, and somebody takes that algorithm, and what they do is to make some minor changes so that instead of detecting objects in general, it can detect lamps or chairs or tables. So that this is an ideal scenario where everybody shares their knowledge. But if there is a backdoor in the original one, thanks to the transfer learning, that backdoor continues to be there. The backdoor will remain there. So, to summarize, you need to be careful whose models you are using and where you are publishing your models with which providers, because there is the technical capability of introducing backdoors to make your systems work differently. So now, in summary, machine learning allows us to create better hacking tools. The authentication authorization can be deceived with or without machine learning. It is possible to steal models, so we need to take care of our privacy. We can perform targeted or massive attacks. We can replicate models without knowing anything about the system. Then we also talked about the manipulation of backdoors and models. And what's very important is that these attacks are more and more practical. And what I mean is that in many cases, the input information needs to be slightly modified so that the system yields the results you want. And this ability is growing more and more. In terms of digital applications, we can modify by 2 or 3% very small amounts. After 600, 700 or 800 requests to a provider, you can actually do it. Just a couple of things regarding the formalization of offensive security. Well, now everyone who wants to use these technologies in technology or in cybersecurity in particular, they should apply the pen testing we are currently applying in order to check how secure they are in terms of cybersecurity. And for that, we have several ways. The traditional one, the more related to academia, creating better algorithms, but then there are others that have to do with cryptography. If you know anything about cryptography, hash algorithms, etc., you will know that certain functions, for example, M5 in hash, an attacker can provoke changes in results. So for this, we can create either better algorithms or use another alternative, which has to do with using several algorithms at the same time, although they are insecure. Why? Because using more than one algorithm, as it happens in many other scenarios, you may have two different inputs and achieve that the system doesn't classify the way it should be. Here you can see X and Y in the function may work differently. This may happen with cracked algorithm, for example M5, and that is quite difficult. In artificial intelligence, this is the same thing. We may have a model that may be attacked with offensive attacks, but with the combination of both, and using the black box, we can create white box and black box attacks so that our system doesn't classify malware correctly. And this is what we are working on now in order to achieve solutions. So these are now the recipes we would need in order to make more robust defensive security against these attacks. We are now defining the so-called rubbish class. One of the usual problems in classification is that whenever we have an input, there is an output within a range of possible values. We have a system that identifies numbers from 0 to 10. So the output will always be a number from 0 to 10. And in terms of security, that doesn't make a lot of sense. The ideal situation would be that 0 would be classified as 0. And if not, we would need to have a different class going through that same way. That's why the rubbish class is being introduced, so that things that are a little bit off the established path go to that class. We are trying to deceive the attacker. This is a classic solution, and many companies are currently doing that, but we need to continue working so that attackers don't gain advantage over the defender. That's why we are using deep learning now. When it comes to privacy, here we have a lot of issues. Many of the references I've given you allow you to obtain models with 90% accuracy in Google. And anyway, as it happens in security in general, we need to understand this as a global architecture. If we are introducing artificial intelligence in order to provide more security, we need to analyze the security of the element itself and be aware that the fact of introducing AI in order to obtain a small percentage of improvement, that may be a global problem. So we need to assess the risk and see whether it is worth it or not to introduce artificial intelligence. So if you work in this, or if you see people or hear people talking, sometimes when we go to the companies, we ask them this kind of questions and they don't know how to answer, because we need to convince them that security needs to be embedded in that cycle, at least in the initial phase of the algorithms, with clever hands or with other tools, in order to understand that in a real situation the attacker will try to deceive our AI system. And if the AI system is aimed at providing security, well, then we are in trouble. This is what I wanted to share. I wanted to insist on the idea that AI is useful. There are many domains. We've been using it in security for about 20 years, and malware detection and traffic controlling. It's not clear what the solution is, but what is clear is that offensive security is clearly advancing, and we need to take decisions in order to know what to do with algorithms and how to make them more secure. So thank you very much for your attention. I will be hanging out here. I will be on Twitter or Facebook, and I will be very glad to answer any questions you may have. Thank you very much.